Just that one. All right, so back to evaluating integrals. We're going to learn the next few sections go pretty quickly. And we're talking about different techniques for evaluating integrals because we're going to need these techniques to be able to apply them. We're kind of limited with what we're able to find antiderivatives of based on the type of function. So there's this idea of substitution, and this is a big, huge technique. You're going to be doing substitution lots, almost every time we do an integral from here on out. Not every time, but very frequently. So what I want to show you first is how this works by, let's first evaluate this integral if we didn't know what substitution was. And I would even say maybe even easier, even when you do learn what substitution is, we know that when we have a product of two functions, we can't just find the antiderivative of that and multiply it by the antiderivative of that. But what we could do is just distribute this, right, by simplifying it first. So let's do that. That would be 5x to the 9th plus 5x to the 4th. And using our power rule, 5 stays there, x goes up a power, divide by the same power. Same thing here, 5 stays there, that's x to the 5th over 5. Now, okay, when we have an indefinite integral, indefinite means there's no limits on there, then that's when we go back to putting the plus c on there. And we might as well just simplify this. This reduces to x to the 10th over 2 plus x to the 5th plus c. Easy enough. But another way to do this integral would be to make a substitution. I mean, I don't know that we really would want to do this here because it was pretty easy to evaluate, but let me just show you how this works with this example. Somebody came, oh, what happened? It beeped. Somebody must have, oh, here we go. So the idea of this is we're going to convert our integral in terms of a different variable. We're going to substitute. We're going to let this part in the parentheses be u. So let's follow the directions here and let's just substitute that in. So this is just u. Whoops, I forgot my 4. Let me move that up. But here's the idea. This is my scratch paper over here. We know a lot about antiderivatives. Most often we use x, but we know that when you see an antiderivative, it can be any variable. If someone said the antiderivative of t squared with respect to t, that would be t cubed over 3 plus c. If someone said I wanted z squared, the antiderivative of that with respect to z, that's z cubed over 3 plus c. And then more about what we call the differential, the little d something. It is kind of important. I'm going to go up here. If you were to write down the antiderivative of w squared, yes, I know what you probably mean. I know you probably mean find the antiderivative with respect to w, meaning w cubed over 3 plus c. But technically, you need to have this differential there because what that's telling you in words, this is saying I want the antiderivative of w basically in terms of w, right? When I say with respect to, that means in terms of. In terms of w. And I know it sounds strange, but there will be a time in 17C next quarter when this will actually have meaning. The antiderivative of x squared, you might say, oh, that's x cubed over 3. But what if I said in terms of y? This is something that we will see in 17C. So for now, what I would say is whatever variable you have here, you're going to see the same differential here. Whatever variable, it's going to be the same thing. And one of the questions I did see come up in class was what happens to the, right, when you do this, what happens to the dt? What happens to the dw? Why does it go away? For now, think of this as, this is like telling you the directions. It's telling you find the antiderivative of this with respect to w. Once you've done that, there's no need to have dw, right? It's a set of directions, basically. My point of all of this is, if we're making this choice to convert this, to call this u, that means what we need to somehow get next to this is a du. We want to have a du, because that would tell us we're going to find the antiderivative with respect to u. Now, where does that come from? Well, what is du? It's part of the derivative. With that substitution, if we took derivative of u with respect to x and get 5x to the fourth, du is right here. And we can think of these at the end of 17a, when we were talking about, what was it, linearizations, if you recall that from 17a. We learned to think of a derivative as two separate things. This notation, this is a small change in u, that's a small change in x. And so we can separate these. We could multiply that dx over to the other side. Okay. And then, now, remember, this is also multiplication. The order of multiplication does not matter. If I want to, you don't have to do this, but if I want to, I could just put the u out in front and put the 5x to the fourth right next to the dx. You don't have to do that, but just to help you see it. But here's the way I like to think about this. 4 quarters, $1. That doesn't even look like a dollar sign. There we go, $1. How many people agree when you're holding 4 quarters and $1, they look different? But how many people agree they're equal to each other in value, right? They're the same. So the way I like to think of this is, in your next step, you're going to exchange this in. 5x to the fourth dx equals du. So we're just going to trade that in for du. We can replace that with du. That's what it equals. Oh, the link. Yeah, let's see. Here's the sign-in form. Yeah. And then, now that you've successfully converted this integral in terms of a u and you have a du, which tells you, okay, now you can find the antiderivative of u to the first with respect to u. That antiderivative would be u squared over 2 plus a constant. U-substitution is a tool to help us get to the antiderivative. Once we found our antiderivative, we want to get this back in terms of our original variable, which was x. So after you find the antiderivative, we're then going to plug this back in. So this becomes x to the fifth plus 1 squared over 2 plus c. Now, the other reason I chose to do this integral 2 ways is I wanted you to notice something here, but I also want to convince you, since this is the same integral, I might have to back this out a little. My claim is that this answer and this answer are the same, because it came from the same antiderivative. Power rule. Remember, the antiderivative of x to a power is you add 1 to that power and divide by p plus 1, and then you divide by that same power. So that was u. If you see u, that's u to the first. So I added 1 and then divide by the same power. You know what would probably have helped if I had written, so from here to here, I am finding my antiderivative. Now, so I claim these are the same. How many people agree they don't look quite the same? They don't look quite the same, do they? So what I want to convince you of is that they are the same. So I'm going to simplify this. Most of you are pretty good at foiling this out in your head. If you foil out the top, x to the 5th times x to the 5th is x to the 10th. You're going to get 2x to the 5th terms, and then you're going to get a 1, and all of this is over 2. And we know that when you have one thing in the denominator, you can split this up. So this is really x to the 10th over 2. 2's cancel there, plus x to the 5th plus 1/2 plus c. Now, do they look the same? Does this look the same as what we did up here? How many people agree they still don't look the same, right? I have to really bring this out. What's different here is I have an extra 1/2 here, huh? And I just claimed that these were the same. In fact, they are the same. And you need to know this. You need to see this because this question comes up quite frequently. Let's say your friend did the integral by distributing first and got this answer. You decided to do a U-substitution. You got this answer. I've had plenty of students over the years who get in arguments because they think somebody's wrong. Because you get an extra 1/2 here. Here's how we justify that these are the same. What do I mean by C? What does C stand for? How many people agree that stands for a constant, right? Do we claim, so when you put plus C here, do we claim that that constant has to be the same as this constant? No, right? It's any old constant. So the idea is we can justify these are the same. If I wanted to, 1/2 plus a constant is just another constant. I could replace this with just another constant, right? And then they would look the same. Now you don't have to do that. You don't have to, but I could justify this as just being a constant so that it looks identical to this one. So just know that if you check your answers, if you're doing some problems from the book and you get the back of the book has this answer, you get this, as long as you're only off by a constant, you're okay. That doesn't mean you're wrong. Okay. I know that can be a little bit troublesome, right? When you see, wait a second, that's not the answer the back of the book had. So I'm just going to put same because we could call this C. The other thing, I guess, to acknowledge, I think I did this earlier, but just to acknowledge this is that how many people agree doing it the first way was a lot easier than using U-substitution, right? Just to simplify first. And so that's an important point to make as well. Just because we're going to have this new technique of U-substitution doesn't mean we, number one, will always need to use it. Number two, we always should use it. Like here, I could use it, but I saw that that was a little bit harder. So keep that in mind, that if there's any way to simplify your integral first, that's probably going to be easier than U-substitution. Now, unfortunately, on my next one, there's no way I can simplify this. This is a product of two things. And we know I can't just find the antiderivative of this and multiply it by the antiderivative of that. And there's no way to simplify it. So here I do have to use U-substitution. And one of the things we'll work on today is how do you know what to let U equal? Whatever we let U equal, in this case, I'm going to let U equal x cubed, which is part of the integral, so that this part right here becomes e to the u, right? E to the u. And what's left over to replace is 3x squared and dx. Excuse me, I need to water. And you kind of think ahead. You say, well, wait a second. If I let u be 3x be x cubed, and I know, so what you're always going to have to do once you make a u substitution is you're going to take the derivative of it and you're going to multiply the dx over. So in fact, most of the time as we get good to it, you're just going to go good at this. We're just going to go straight to this. You're going to do du and then just automatically tag on the dx over here. Okay, you can skip this part. And you'll notice then that, what do you know? 3x squared times dx is exactly du. So on my next rewrite here, I could replace this and this. I'm going to exchange in for a du. Which is good because just in the same way that the antiderivative of e to the x dx is e to the x, the antiderivative of e to the u du is going to be e to the u plus a constant. And once I find my antiderivative, I put my u back in, e to the x cubed plus c. So how did I know to, why did I take this as my u? Why this? It's because the derivative right here shows up in my integral, because derivative is also in my integral. Right, that was my u and the rest of it was du. That's kind of the thing to think about when you're doing u substitution. Okay. Yeah, okay. So with that in mind, if how you should be choosing your u is the derivative shows up somewhere else, whenever I see an ln of x in an integral, what do I hope to see somewhere else? What's the derivative of ln of x? Exactly, it's 1 over x, because that tells me that if I let u equal ln of x, just ln of x, I can see the derivative right there, huh? The derivative of that, and this, I'm going to take the short version now. I know it's du dx, but the derivative of this is 1 over x, and we're just going to move the dx over. So if I now envision this integral, let me just do first a rewrite just in terms of x still. Right, if I just simply rewrite this, like think of this as 1 over ln of x squared times 1 over x dx, I can now see that this is going to be 1 over u squared. And all of this now just gets exchanged in for a du. Whoops, move that out. It definitely takes practice. That's why we've got to do a lot of examples to get good at u substitution. Now I've converted it to u's and du's. So now I'm finding my antiderivative. And so we're going back to that technique. Remember, if you wanted to find the antiderivative of 1 over u squared or 1 over x squared, you want to bring that up. You want to make that u to the negative 2 du first, and then do your power rule where you add 1, divide by the same number. This is really the same. U to the negative 1 over negative 1 is the same thing as negative 1 over u, isn't it? Negative 1 over u. And so then I would replace back with what u was equal to. So you're always thinking, unless you see a way to simplify it first, right? You're always thinking, is the derivative of one part of this integral somewhere else? And so having sine and cosine in the same integral is a good thing, right? Because they're each other's derivatives pretty much, right? So the derivative of cosine is negative sine, and the derivative of sine is positive cosine. But there is a correct way. Like, let me just show you, like, and sometimes you have to go down this road until you realize it leads to a dead end. You start thinking, well, I know the derivative of cosine is sine, so what if I let u equal cosine? Here's the problem with that. The derivative of cosine is negative sine of x times dx. But what do I have in my integral left over? I have, first of all, I have 1 plus sine x, but it's not times dx. This is dx over that, right? This dx is in the numerator. I don't have negative sine x times dx left over. There's no way I could exchange that in because it doesn't show up here. So that would not be a good choice for you. What would be another good choice? And let me show you more reasoning on how you choose your u. Certainly, if I let u equal sine x, du is cosine of x times dx, which is exactly what we have here. But then here's the other thing. Why not just take this 1 as well? Because the derivative of 1 is 0 anyhow. So another kind of guideline for what you should do for u, take as much as you can get away with, okay? I could have just done sine, and then I would have had 1 plus u on the bottom. But if I just take the whole denominator here, I can still satisfy the du. The bottom is u, and cosine of x times dx is exactly du. So that's going to turn into du. Okay. And then, okay, there's another question. On the previous one, I had 1 over u squared, and you saw me bring that up as u to the negative 2. But remember, this is your one exception. This is, if you brought this up as u to the negative 1 du and try to do your power rule, you're going to end up with u to the 0 over 0, which is no good, right? So this is your one exception. What's your antiderivative of du over u? Also known as, if it helps, just put a little 1 there. 1 over u du is whose derivative? One over u times the derivative of u is ln's derivative. Yeah. 1 over u times du is ln's derivative. So this is going to be ln. Recall earlier, we have to put an absolute value to make sure that we're not taking log of a negative number. And then this becomes ln of, my u was 1 plus sine of x plus c. Okay, so we've done 4 of them now. And all 4 of those had one thing in common, even though they were completely different integrals. They had one thing in common, is that once I took the derivative, once I made the correct choice for u, the derivative showed up and it was just like a perfect match, right? I could just exchange that out for a du. Sometimes we're not that lucky. Sometimes it doesn't come out exactly how we want it to. And sometimes we can still proceed. We can still make it work out. So look at this next one here. I have x cubed, integral of x cubed times the square root of x to the 4th plus 7. And other good suggestions for what I should let u equal are things in parentheses. And I would argue it's under a square root, which means it's really raised to the 1/2. Things in parentheses are often the correct choice for u. I think I mentioned this before, but unlike last quarter, especially unlike last quarter with derivatives, things are less clear cut. I can't give you things that will always work with antiderivatives. I can give you more of suggestions, things that you might try this. If that doesn't work, try this. It's not as clear cut. Now, that's promising for a choice for you because my derivative is 4x cubed dx, which is close to what I have left, huh? It's close to what I have left. In fact, let's go ahead and let's do this. Let's rewrite this. This is now u to the 1/2. That's this term. And let's go ahead and why don't we just really emphasize this? Let's put the x cubed next to the dx. Let's just put these two together. All right. We have a decision to make here. I watched class on Monday. I saw how Professor Burke explained this. And here's the deal. When it's not a perfect match for just replacing this with a du, there are about 3 or 4 slightly different variations on how to explain what to do next. Professor Burke did one of those 4 techniques. How many people are interested in learning what I think is the most efficient technique, the fastest technique that will get you to where you need to be? And the caveat to that is, even if it's a little different than what Professor Burke told you, and if you're open to that, know that she doesn't really care. She's just picking a way to explain how to do it. It really doesn't matter as long as you're getting to the same place. How many people want to see what I think is the fastest way to do it? Okay. Bella, you're funny. Okay, I'll show you a way, not the way, a way. But yeah, you're right. Since I think it's the best way, I'm going to say maybe, well, I think this is my favorite way. Okay. And some of you might remember what I'm actually going to do is the wishing technique, which if you had me for 17A, I remember we did that when we were doing some limits, some sign limits. Okay, so here's let me explain this to you. Here's the idea. If I had a 4 here, if there was a 4 there, then do you see that I could just exchange that in for du, right? So I'm going to wish for a 4. I wish I had a 4. I wish I had a 4. I wish I had a 4. There's my 4. Okay. Now, of course, we know you're not allowed to just put a 4 there. That's changing the problem. So I'm going to compensate by outside the integral, because remember, any constant can come outside. I'm going to put a 1/4. Because what is 4 times 1/4 is nothing more than just 1. So I'm not changing the problem. Okay. By doing that, though, here's where I've now figured out. The 1/4 here can stay there. This is now a perfect match, so I can just call it du. And I've now converted it to u's and du's, and so I can proceed with the integral. Let's finish the integral, and then we'll come back and talk about this. So to finish this integral off, you would do your power rule. Raise 1. If I divide by 3/2, that's the same as multiplying by 2/3. And then final step would be to replace my u with what it was. So that'd be 2/3 x to the 4th plus 7 to the 3/2 plus c. So, okay, now let me go back and explain this. Here's the only one drawback of the technique that I have done here. Notice I used a different color of pen. I think that comes out on Zoom. I used a red here because one of the drawbacks will be if you stick with the same color and you go back and look at your work and you try to study for the test, you're going to say, wait, where the heck did that 4 come from? What's going on here, right? You're going to get confused of where that 4 came from. So if you don't have a different color of pen, my technique, what I do is anything I wish for, I circle. And that's my cue and your cue that wasn't there. I put that there. Okay. And so I'm going to just put a little thought bubble here. Wish, whoops, that's not how you spell wish. Wish for a 4 so that you can get this and compensate with a 1/4 outside. Exactly. The way what Maya is describing, that's how Professor Burke did it in class. Is she made 1/4 du equal to x cubed dx, but then once you make this 1/4 du, what do you have to do? You have to pull it out anyhow, right? So my claim is I get to hear faster by doing that. Let me give it and I'm definitely, I always say this, if I show something and you say, you know what, I kind of like the way I was doing it before, totally, by all means, that's fine. That's fine. Okay. I'm just giving a suggestion here of the way I think of it. And if it works for you, then great. Right. So let me try another one though, before we, maybe I can get some more convincing here. Okay. I said things in parentheses are a good choice for you. So let's go with x squared plus 6x plus 1. I don't need to take the power because I could just make that u to the 4th. My du is 2x plus 6 dx. And I realize that what's left over is an x plus 3 dx, which is exactly what I would get if I factored out a 2 here. Okay. So bottom is already taken care of. That's u to the 4th. I have an x plus 3 here. The d, you know, with fractions, sometimes they put the dx in the middle, but if you had to put it somewhere, it goes in the top, right? And I realized that what I have left over is only x plus 3 dx. I was hoping to see 2 times x plus 3 dx. So what do I need to wish for? I want to wish for a 2. So I'm going to put my 2 there. I'm going to circle it just to emphasize that I put that there. And I'm going to compensate outside with the reciprocal of that 1/2 so that the net effect is only 1. The 1/2 stays there. This whole entire numerator now I can just exchange in for du. And I have 1/2 du over u to the 4th. So then I could bring this up. Remember, it's only ln if it's 1 over u to the 1st. If it's anything other power, then you're going to want to bring that up first. And then do your antiderivative. Add 1, divide, and then replace in. I guess I'll just leave it like that. Let's try some more. Lots and lots of practice will make us better. Next integral is cosine of root x divided by root x. And I said things in parentheses. I mean, I guess that's in parentheses here. So I certainly wouldn't want to let u equal the whole cosine, because you have to think ahead. If I let u equal the whole cosine, du is going to have a sign in it. And I don't have any more signs, right, that could accommodate that. So our only hope here, I think, is to let u equal root x. Now, question is, which root x do we mean here, right? Well, I'm actually meaning this one here. But how is this one going to get taken care of? Well, let's take our derivative. The derivative of root x, which is x to the 1/2, is 1/2 x to the negative 1/2 dx. And if I rewrote my integral, if I assumed that this was the one that I wanted to be u, what I could do is rewrite this, bring it up here. That's the same thing as x to the negative 1/2 dx. That's this term right here. I just brought it up. And why did I do that? Because look, du, what I was hoping to see, so I could trade it in for a du, is 1/2 x to the negative 1/2. But in my integral, I only have x to the negative 1/2 dx. So what do I want to wish for now? What do I wish I had here? A 1/2. Yeah, I want to wish for a 1/2. So this time I want to compensate with a 2 outside. Whatever comes outside, whatever you compensate with, just stays there. This is now cosine of u, and all of this is now a straight up trade-in for du. Your antiderivative of cosine of u is sine of u. And then my u was root x. Done. Questions on any? Yeah. All right, so see, we've done a few now. So try number 8. Think about what you would let your u equal, knowing that whatever you let u equal, you're going to take the derivative of it, and you need to see something close to that somewhere else in the integral. So what's a good choice for u? Well, the derivative of e to the 4x is e to the 4x times 4. So I know that I want to have one of these u's, and many times, I told you the rules are not so clear cut, but if you've got a fraction, a lot of times the derivative would be at least part of the bottom, if not the whole thing. This time it's going to work, because if I let u equal the whole bottom, the derivative of e to the 4x is, again, e to the 4x times 4, which is really 4e to the 4x dx. And see, now I'm going to, not do the intermediate step of rewriting this. We know this is going to be u on the bottom. This, what do I need to wish for up here? I need to wish for a 4, right? 4x e to the 4x dx is exactly du, and I'll compensate with a 1/4 outside. The whole entire numerator is du. The whole entire denominator is u. And I think we saw this before. This is like 1 over u to the first. So this is going to integrate to ln once again. Well, ln of u, which is oh, can't see that. Okay, a couple more examples. So get us to an even 10 examples in class. That's pretty good. Hey, yeah, actually, I like this one. I must have picked this for a reason, because I just got through on the last one saying, oftentimes you would want to let u equal part or most of, or maybe even your whole denominator. That's often will work. But can you see here that there's no way that would work on this next one? If I tried to make the same choice, my du is going to be 4e to the 4x dx. And to be clear now, because what do I have left over? I have an e to the 2x times dx, right? Could I wish for something and get to this? I could. But what would I have to wish for? I would have to wish for, here, I'm going to show this on here. I would have to wish for, so if I tried to let the bottom be u, and this was e to the 2x dx on top, I would have to wish for not only a 4, but I would have to wish for an e to the 2x, wouldn't I? So that would become e to the 4x, and then compensate outside. Here's the deal. While in life, you can wish for whatever you want to, for these integrals, you're only allowed to wish for constants. So I'm going to X this out and say, can only wish for constants. Okay, so yeah. So that would not be allowed. And so here's what I'm showing you is that sometimes there's things that doesn't always work. You can't settle on a single rule that's going to work every single time. So instead, here's what we're going to do. Assuming that this will become du, this is going to turn into du, what's the most I could let u equal? Assuming that the numerator was going to become du, the most I could let u equal is an e to the 2x, right? Because the derivative of e to the 2x has e to the 2x in it. And that's actually going to come from here. If I creatively think of e to the 4x as e to the 2x squared, and let u be this one right here, whoops, there we go, e to the 2x, du is 2e to the 2x dx, which I can now make work by only wishing for a constant here. I only have to wish for a 2 here, and then do a 1/2 on the outside to compensate. You can't wish for an A, sorry, only numbers. All right, so then this turns into 1/2. This is now du. And then what do I have on the bottom? It's u squared plus 1. And do you recall this? Do you spot this one? This is the same if I wrote it like this, 1 over u squared plus 1 du. What's the antiderivative of that? It's not an ln, right? It's only ln if it's 1 over u to the first. This one is arc, I think that's what, yeah, arctan. This is arctan, also known as tan inverse. So it's going to be 1/2 tan inverse of my u, which is e to the 2x. Okay, so last one here. And what I want to show you here is, this is like a little bit of a twist on U-substitution and an option if we kind of get stuck, okay? So I have the x times x minus 1 all raised to the 7th, and I want to find the antiderivative. I will go to my general guidelines, and not to be followed 100% of the time, but usually things in parentheses are good choices for u. So I'll let u equal x minus 1. du, the derivative of x is just 1, so du is just 1 times dx. Du is dx. And so the issue here is not wishing for anything. This is now u to the 7th. dx is a straight up exchange for a du. The issue here is I have a leftover x term, right? That is unaccounted for. Leftover x term. Okay. And what I want to show you is that if you do a U sub and you convert it to U and you end up with leftover X's, some expression with X, sometimes there's still a way forward. And you don't have to give up and start over. Sometimes there's still a way forward. Remember that my goal is to turn this entire integral in terms of U's and DU's. And what's my only equation that links those two is this right here. So if U is equal to X minus 1 and I need a replacement for this X, that means X is equal to U plus 1, right? If I just move that over. And I can now replace this. I've got a replacement that I could come back here and replace this X with U plus 1. Replace with U plus 1. So some teachers call this back substitution because you made your substitution here and then you went back to it and solved for X in terms of U. So like some teachers call it back substitution. I just call it the way I see it. U-Substitution with leftovers. If you get leftovers, you got to clean them up, right? You got to clean them up. And this won't always be possible, but if you can do it, that's how you could work out the integral. So then the X is now U plus 1, U to the 7th du. And I've at least successfully converted everybody to U's and DU's. Now notice this looks kind of similar to what we started with, but here's a big, big difference. Here, there's no way I can distribute an X into X minus 1 to the 7th unless I FOILed it out. But here, U to the 7th is really easy, right? I could just distribute that in here, giving me U to the 8th plus U to the 7th, and then do my power rule. So it's X minus 1 to the 9th over 9 plus X minus 1 to the 8th over 8 plus a constant. All right, so that's how U-Substitution works. I would strongly suggest, well, I'm sure she gave you a bunch of book problems to practice, so I would definitely do those. I was going to look on my website. I bet you I have a bunch of practice ones too. Substitution, more substitution practice. No, that's not going to be what I want. Give me 1 second here. I need to move this to this. Okay, so if you're looking for some more practice problems in addition to what she's given you, let me just quickly share my screen here as I need to move this over to my new I was on my website, which I can no longer find. Let me go back. I need to move this to my new, you should be looking for everything on the new book that we're using now, but on my old book, 17B old book, I have some U-Sub practice here. It was a different chapter section, U-Sub practice with solutions. So if you're looking for some practice problems that you could go check your answer with U-Substitution, there's 15 more problems right there. So, all right.